We are diving straight into VGGT,
Yeah.
Visual Geometry Grounded Transformer, a massive 1.2 billion parameter model that's really shaken up how we think about 3D reconstruction.
Yeah, if you work in 3D vision, you have to read this paper. The main takeaway, and you should just pocket this right now, is this. VGGT is a huge feed-forward transformer, and it's designed to completely ditch that old reliance on slow, iterative stuff like bundle adjustment.
Right.
Instead, it just infers all the key 3D attributes. We're talking camera pose, depth, 3D points from, up to hundreds of images in one single fast-forward pass.
And that speed is the headline here. I mean, this system gets state-of-the-art results like 88.2 AUC at 30 on CO3D V2 in literally less than a second.
It's wild.
We're talking 0.2 seconds for 10 frames. This isn't some small improvement. It's a completely neural solution that shows a massive data-trained transformer can actually learn complex geometry faster than traditional algorithms can compute it.
And that speed, plus its ability to generalize, that's the real breakthrough for any kind of practical application. It's built on a standard large transformer, kind of like what powers LLMs, which proves you don't need a super custom bespoke geometric pipeline. You just need scale and data.
Okay, so let's unpack this. Let's start with the problem VGGT is trying to solve. For anyone who's had to deal with big 3D projects, what was that necessary evil of the old way of doing things?
The old paradigm, it was all rooted in classic visual geometry methods. Structure from motion, or SFM, and multi-view stereo, MVS. These systems are, they're complex, they're sequential, and they are incredibly expensive computationally because they lean so heavily on iterative optimization.
And the big one there is bundle adjustment, right? BA.
That's the elephant in the room, exactly.
For anyone listening who doesn't live and breathe 3D, can you just remind us why that iterative bundle adjustment step is such a performance killer?
Yeah, of course. So imagine you've taken, say, a few hundred photos of a building. SFM gives you a first guess of where the cameras are and where the 3D points in the scene are. But these are just initial estimates.
Okay.
Every time you add a new photo or refine a point, you realize things don't quite line up perfectly across all the views. BA is that huge nonlinear optimization that comes after. It painstakingly refines all the camera positions and all the 3D points at the same time to minimize the error. It works, but it's like retuning an entire orchestra after every single note.
Huge resource drain.
A massive one, especially when you scale up. And even when machine learning started creeping in, it was mostly just helping out, doing feature matching or single image depth prediction. Even the really modern stuff like VGG-SFM, it still has differentiable BA baked in, which just adds another layer of complexity.
So geometry still drove the whole process.
Exactly. And look, there were attempts at pure neural geometry models like DST3R or MST3R. There were steps in the right direction, for sure, but they were stuck doing pairwise reconstruction.
Only 2 images at a time.
Right, which means you're right back in post-processing hell. You have to somehow fuse all those little pairwise results and then globally align them to get one coherent point cloud. It wasn't truly end-to-end.
That is exactly where VGGT makes its big leap. It just gets rid of that entire multi-stage process. It handles up to hundreds of views all at once in a single forward pass.
That is the critical departure. No more costly, iterative cleanup just to make the results usable. The comparison is pretty stark. Other neural methods like Flare might do 10 images in half a second. VGGT does it in 0.2 seconds. The traditional methods, you're looking at 7 to over 20 seconds. Easy.
So the whole philosophy is different.
Completely. Their point is that the performance doesn't come from some clever 3D architectural hack. It comes from taking a standard big transformer, think GPT or Dino, and just training it on a colossal amount of 3D annotated data. Scale itself becomes the geometry engine.
Okay, let's get into the architecture. Starting with the input. If they're not using custom 3D layers, how do they get the images into the model?
They pretty much follow the standard transformer playbook. The input RGB images are broken down into patches, which become tokens. But what's interesting is their choice of tokenizer. They didn't just use a simple convolutional layer.
What did they use?
They specifically used a pre-trained Dynova 2 model to generate the tokens. And they found it gave them better performance and, really importantly for anyone actually training these things, much better training stability. That pre-learned visual knowledge from Dynova 2 gives the model a huge head start.
So you have your tokens. The core transformer has 24 layers, and the big novelty here is what they call alternating attention, or AA. This has to be the secret sauce for fusing all that multi-view information without optimization.
That's it. AA is the clever part that connects the 2D pixel world to the 3D scene. The layers alternate strictly between two kinds of self-attention. First, you have frame-wise self-attention.
So focusing only within one image.
Right, maintaining the local context. Then, in the next layer, it switches to global self-attention. This integrates information across all the frames at once, letting a token from image 1 talk directly to a token from image 500.
It's like forcing the network to zoom in on the details and then immediately zoom out to see the big picture over and over.
Yeah.
Did they prove this was actually necessary?
Oh yeah, they did ablation studies. When they tried versions with only global self-attention or other mechanisms like cross-attention, the performance dropped off a cliff. For point map estimation, the full A architecture got an overall score of 0.709. Global self-attention alone was way worse at 0.827. So yeah, that continuous switching between local and global is key.
Okay, so the architecture makes sense, but how does a pure transformer, which usually lives in 2D, anchor itself in a 3D world? It needs a coordinate system, right?
It does. They establish a really clear anchor. The very first image in the sequence, which they call gone, defines the world reference frame. And to make sure the network knows this, they append special learnable camera and register tokens just to that first frame's tokens.
So everything is relative to that first camera.
Everything. It gives the entire system a single unified reference point to predict all the cameras, depth, and points against.
And then comes the prediction itself. They predict 4 things at once, which the paper calls over-complete prediction. You've got camera parameters, depth maps, 3D point maps, and tracking features. That sounds redundant.
It does, right? I had the same thought. It seems geometrically redundant because if you know the camera pose and the depth map, you can just calculate the 3D point map with simple math.
So why predict it separately?
Because the multitask training proved it works better. They use a combined loss function for all 4 tasks, and the ablation studies were crystal clear. Explicitly training the network to predict all 4 interrelated things gives you the highest accuracy across the board.
So the redundancy actually helps.
It seems to regularize the network and forces it to learn better, more robust internal features. Forcing it to solve all 4 problems at once makes it better at each individual one.
It sounds almost too good to be true. Is there any catch? Like a scenario where the old, slow methods still win?
That's a great question, and the answer is a bit nuanced. If you look at the raw feed-forward performance for camera pose, VGGT is basically as good as or better than other neural methods and often beats optimization-based ones like VGGSFM v2. And it generalized incredibly well to the real estate 10K dataset, which it wasn't even trained on.
So for pure speed, it's a clear winner.
No question. But the authors also showed something else really interesting. While VGGT is fast, it also provides the absolute best possible starting point for the traditional methods.
So it's not just a replacement, it's an accelerator.
That's the key technical detail. When they took VGGT's predictions and then just ran a short standard bundle adjustment on top of them, what they call VGG2 plus BA, that combo yielded the highest overall accuracy. It hit 91.8 AUC at 30 on CO3DV2.
Because it's starting from a much better place. Yeah. It skips all the painful initial setup that usually bogs down BA.
Exactly. It bypasses all that slow initial triangulation and refinement, so you get the best of both worlds. Super accurate neural initialization, followed by a quick final geometric polish. And that whole combined process is still incredibly fast, like 1.8 seconds total.
Which is a huge improvement over a traditional pipeline that can take 10 seconds just to start converging.
Yeah, and they saw the same thing on the IMC phototourism benchmark, which is notoriously tough for neural methods. VGGT plus BA was way better than VGG SFM v2 there, proving it can handle really complex real-world scenes.
What about the dense outputs? For multi-view depth estimation on the DTU dataset, how did its multi-image approach compare?
It was a blowout. VGGT was dramatically more accurate than older methods like DUSD3R that just average a bunch of pairwise results. It cut the overall chamfer distance score from 1.741 way down to 0.382. That's a massive improvement, and it really proves the value of training on the full context of many images at once.
And here's that interesting bit of irony again. We said the model is trained to predict all 4 things jointly. But for the dense point map output on the E3D benchmark, they found something counterintuitive during inference, right?
They did, and this is a great little insight. They found that if they took the independently predicted depth map and the camera parameters and then just used standard 3D math to create the final point cloud,
it was better.
It was more accurate. It got a 0.677 overall score compared to the 0.709 from a specialized point map head.
Wait, so the network is better at predicting the ingredients for the 3D geometry, the depth and camera pose, than it is at predicting the final 3D geometry itself.
Exactly. It suggests that while multitask training is crucial for learning good internal features, for the absolute highest accuracy output, it's still better to decompose the problem into its geometric fundamentals, pose and depth, and then combine them mathematically at inference time.
That's a fantastic practical tip for anyone designing these kinds of models. It all points to the fact that the features VGGT learns must be incredibly robust.
Right.
And we see that when they use it as a backbone for other tasks, not just for reconstruction.
That's a huge validation of their whole design philosophy. Take dynamic point tracking, for example. They took an existing model, CoTracker, which is designed to track points on moving objects, and they just swapped out its feature extractor for VGGT's pre-trained features.
And the result was
An immediate, significant improvement across the board on the TAP-VID benchmarks. A key metric, delta-vis average, jumped from 78.9 up to 84.0. This means the features it learned on static scenes generalize surprisingly well to tracking points in dynamic moving videos.
And they did something similar for novel view synthesis, or NVS.
Right, predicting what a scene would look like from a new viewpoint. And crucially, their NVS version did not need to know the camera parameters for the input images, which is a requirement for a lot of competing methods. And even though they trained it on a smaller data set, it still achieved competitive results.
One thing that really surprised me was the single view reconstruction. I mean, usually getting 3D from one image involves a lot of tricks.
Yeah, but the beauty of a general transformer architecture really shines here. VGGT just naturally supports a single image as input. The global attention part just defaults to being frame-wise attention. And even with zero specific training for this task, the model produced surprisingly good 3D point maps from really tough inputs like paintings and sketches.
That just shows how much abstract knowledge is really baked into those 1.2 billion parameters.
It's learned something fundamental about 3D structure that goes beyond just photorealistic scenes.
So thinking about actually deploying this, scalability is always the next question with these huge models. How do the runtime and memory scale?
They scale quite gracefully, which is critical. Processing 10 frames takes about 0.14 seconds. Scaling all the way up to 200 frames takes about 8.75 seconds. Memory usage is also predictable, going from under 2 gigs for a single frame to around 40 gigs for 200 frames at a decent resolution.
And that flexibility is key for engineers, right? You can do the lightning-fast single pass if you have a big GPU, or you can fall back to a sequential frame-by-frame prediction if you're on a more constrained system.
Exactly, and that sequential method only adds a tiny bit of time and memory per frame. Now, the authors were upfront about the current limits. It doesn't handle things like fisheye or panoramic images yet. And the quality can degrade with extreme camera rotations or, if a person is deforming a lot in the scene.
But their point is that the architecture is flexible enough to adapt.
That's their argument. Because it's a general transformer, you can address these things by fine-tuning on specific data sets. You don't have to go back and completely re-engineer a rigid, complex geometric pipeline. It's built to be adaptable.
At the end of the day, it really feels like VGGT demonstrates a profound shift. We're seeing raw data scale and flexible neural architectures starting to outperform decades of very carefully engineered geometric optimization.
It's a major milestone.
And this leads us to the final provocative thought to leave you with, which comes straight from the paper. The authors mentioned that using differentiable bundle adjustment during large-scale training was just computationally impossible. It slowed down each training step by 4x.
Right, it's just too slow to use for supervision at that scale.
So, if optimization provides the ideal geometric signal, but it's too slow to use for training these massive foundation models, then maybe the next big step in 3D vision research isn't about refining the geometry loss functions. Maybe it's about figuring out how to efficiently scale unsupervised training to use that powerful differentiable BA, not as a loss, but as a weak supervisory signal when you don't have explicit 3D ground truth.